Hey guys, what's up? It's Eric with Advanced Level Automotive. Welcome back to another video. Welcome back to another case study. Right behind me I have a 2014 Buick Verano. It's got the 4-cylinder, 2.4 liter ecotec engine in it. Customer complaint is that the vehicle will stall while he's sitting in traffic, and when he tries to accelerate, the vehicle just feels like it's chugging along. So anyways, vehicle's here. Let's go ahead and get started. All right guys, so we're inside the vehicle. I'm gonna go ahead and start it up. As you can see, the check engine light is illuminated. Wait till all the other lights go off. You'll see we have the check engine light on. And right now the engine seems to be idling fine. So far there aren't any issues. Let's go ahead and get the scan tool up here. I've got the Maxi Sys. We're gonna go ahead and scan for codes in the engine control module. This is a 2.4 liter. Let's go into trouble codes. And we have two different codes. P0010, which is a intake camshaft position actuator solenoid valve control circuit. And then we have another P0011. This is for the intake camshaft position system performance. Now these two codes are related to the intake side, so it's real important to note here that we don't seem to have any codes for the exhaust side, only for the intake side. Now the reason I bring that up is because generally the first thing I like to check when I get these types of codes is the oil level. The reason behind that is because whenever the engine oil level gets low, the variable valve timing system cannot operate properly. But usually when we have a problem with low engine oil level, we also set codes for the exhaust side. Now, even though I don't see codes for the exhaust side, I still think it's really important for us to just check the engine oil level and also the oil condition. So let's do a quick check under the hood, check the engine oil level, and see what the oil looks like. All right guys, so we're under the hood. I went ahead and I pulled the dipstick out. I've already wiped it clean with the rag. I'm gonna go ahead and stick it back into the dipstick tube, and we're gonna get a oil reading. And pull it back out here, and then we'll just lay it up here. See if we can get a good view of it. Now looking at that, it definitely looks like the oil level is full, and also the oil doesn't look like it's in real bad condition. I mean, it's probably due for an oil change, but it's not severely black or anything like that, so the oil level looks okay to me. Let's go ahead and put this back in and go back inside the vehicle, get back to the scan tool. All right guys, so we are back inside the vehicle. Like I said, I just wanted to check the engine oil as a rule of thumb. I really didn't think that we were gonna have a problem as far as low engine oil level. And again, the reason behind that is because I didn't see any codes for the exhaust side. We only saw codes for the intake side. So now that we've eliminated that as a possibility, we can move forward with diagnosing this vehicle. So, okay, so looking at these two codes, the next thing that we want to do is we want to determine what these codes actually mean. So of course we can take a look at the description, and if you read this top one, it's being pretty specific about what it's talking about. It's saying that the actuator solenoid valve control circuit. So this code right here is what we would consider an electrical code or a circuit code. And what I mean by that is that the way this code gets set usually is because the computer is monitoring the voltage at the control circuit, and it's not seeing the voltage it should be seeing when it wants to see it. Now, as opposed to this code right here, now this code is a little more generic. If you read it, it says intake camshaft position system performance. This code was set as a byproduct of this code. So what that means is that more than likely there's a problem with either the solenoid or the circuit to the solenoid, and because that solenoid is not able to function, the intake timing is not able to advance or retard the way the computer wants it to. So that's what this code means. What we can also do is, with this code, we can go ahead and hit the search function, and this thing will actually search the internet for a code description. Now we can choose a website. I'll just choose this one here, and it'll give us more information about this specific code. So if you look here, it tells us, well, it recommends a Scanner Danner video, but scroll down, let's see if we can find some information. All right, so here's a code description. You'll see it says the camshaft position actuator is attached to each camshaft and is hydraulically operated in order to change the angle of the camshaft relative to the crankshaft position. Now it says that the camshaft actuator solenoid is controlled by the control module, and the control module sends a pulse width modulated signal of 12 volts to the camshaft actuator solenoid. Now this solenoid controls the amount of engine oil flow to the camshaft actuator. and the camshaft actuator can change the camshaft angle a maximum of 25 degrees. So this system is pretty straightforward. I mean, if you want, we could pull up a wiring diagram and I could probably explain it in a little more detail, and I'll show you how we can test it. All right guys, so a real quick check that we can do while we still have the scan tool connected. We can go to inactive test, and I believe there should be an active test for the camshaft actuator solenoid, if I'm not mistaken. Right here, camshaft position actuator system. And the one we're dealing with is going to be the intake. It says here, make sure it's in park, set the parking brake, block the drive wheels, hit OK. Alright, so now that we have this test pulled up, we can go ahead and start increasing the percentage. And what that's going to do is it's going to activate the solenoid, and we're going to see if it matches the camshaft position. So if we look, we've set this to 10. Now looking at the intake camshaft position, you can see we're pretty much matching our command. We can go ahead and increase it again. We'll move it up to 20. And you can see that we're matching our command. And this thing just timed us out. The test only lets you run it for 30 seconds, but in that time we were able to see that everything was functioning properly. It looks like the problem that we're dealing with has to be an intermittent problem, because right now the vehicle seems to be idling fine. And when we use the actuator test to command the solenoid open, we could see that the command was actually matching the position. So anyways, that was just a quick check that I wanted to show you guys. Let's go ahead and move over to the wiring diagram. All right guys, so we've got the wiring diagram pulled up over here. If you look right over here, you'll see the camshaft position actuator solenoid valve. Now this is a pretty simple circuit. If you look, we have 2 wires connected to the solenoid, and if you pay attention, both of these wires actually go back to the engine computer. So if you follow this box down, you'll see here on the side it says engine control module, and if you follow this one up here, it says engine control module as well. So looking at this wiring diagram, it's pretty simple to determine circuit design, because if you look at this diagram, GM was actually kind enough to draw what was happening inside of the engine computer. So if you look down here, you'll see that this is actually a constant ground inside of the engine computer. Now this ground is always a ground, even when the ignition is off and even when the solenoid is energized. This ground is just always a ground. Now if you follow this other wire, which is the gray and blue wire, you'll see that internal to the computer we have a switch. Now the way this is going to work is whenever the engine computer wants to command the solenoid to come on, it's going to close this switch, which is going to provide a power source through this gray and blue wire, which is going to go through the coil winding of the solenoid, and it's going to come out on this violet and brown wire, which is going to ground inside the computer. Now what's real important is if you look up here, you'll see they drew some square waves. What they're trying to tell you is that this signal, or this power source, is actually a pulse width modulated signal. And what I mean by that is this switch is going to close and open multiple times very rapidly at a certain frequency. Now the reason they do this is because it's a way of being able to control the solenoid more precisely. So using the pulse width modulated signal at a certain frequency, they can hold the solenoid at a specific position, which allows them to have more control over how much oil flow is going to go to the camshaft actuator. Now testing the circuit is pretty straightforward. Of course, we're going to want to go ahead and put a lead here on the gray and blue wire at the solenoid, and what we want to make sure is that whenever we're commanding the solenoid to come on, we're getting a pulse width modulated signal here. On the same token, what we want to do is put our meter on this violet and brown wire at the solenoid, and we want to make sure that it's providing a good ground. So that's probably what we're going to do next. We're going to go ahead and hook up the lab scope on 2 different channels. We're going to drive the vehicle. We're going to wait till this thing acts up, and then we're going to see if we're missing our pulse width modulated signal, or we're going to see if we're missing our ground. And if we see that we have both things here, then we know more than likely we have a problem inside of the solenoid. So let's go ahead and do that. All right guys, so before I go back to the vehicle to do any testing, I really just want to bring up a real quick point, and this topic can be left open for discussion because I would really like to get your guys' opinion or knowledge on this matter. Now, if you remember, the code that we got was a P0010, and the description on the code was for intake camshaft position actuator solenoid valve control circuit. Now, generally with control circuit codes, the reason they get set is because the computer is monitoring the control circuit for a voltage, and it wants to see that there is a voltage there whenever there's supposed to be a voltage. Now, if that voltage is missing, then the computer knows that there's something wrong with the circuit, and it sets the code. Now, when I look through this code description, It doesn't really give me specifics on how this code is set. Really, the only thing it tells us is that the ECM detects that the commanded state of the driver and the actual state of the control circuit do not match for greater than 5 seconds. Now, if we go back to the wiring diagram, again, we've already determined that this is a power side switch circuit. Now, the reason I'm bringing this up is because unlike the more typical ground side switch circuit, let's say, for example, the Evap Purge solenoid. I've got the diagram for the Evap Purge solenoid pulled up right here. Now, this Evap Purge solenoid is a ground side switch circuit. So if you look, you'll see that there's a fuse right here, a 10 amp fuse. So whenever the ignition switch is turned on, power comes from this fuse, goes through this wire, reaches a solenoid, goes through the coil winding of the solenoid, comes out on this wire, and goes back to the engine computer. Now, of course, the engine computer has the ground internal to it, but this ground has an open switch. So at this point in its normal state, this coil is not energized. Now, the way this works is that whenever the engine computer wants to turn on this solenoid, it's going to close this switch to ground, and that's going to allow the current flow to happen. Now, with this design, if we get a control circuit fault code, the reason that code gets set is because whenever this switch is open, there should always be 12 volts here, as long as the ignition is on. And the reason for that is because this is a fused power source. This has power on as long as the ignition is on. Power should be going through the circuit, going through the coil winding of the solenoid, and reaching the engine computer at this pin. Now, we could say the engine computer has an internal voltmeter, and it's always looking for that power because it wants to know that that power is there and ready for it for when the computer wants to ground the circuit and energize this coil. So let's say we have a problem in the circuit, or let's just say we unplug this solenoid. If we unplug this solenoid, this 12 volts is not going to reach the engine computer, and it's automatically going to set a fault code for a control circuit. The same could be said if we had an open in the wire, or if we had some type of short to ground. Anything that's causing this power not to reach this engine computer will set the code, because the monitor is inside the computer watching for that 12 volts. Now, the reason I bring this up is because I know how this works on a ground side switch, but if we move back over to the camshaft actuator solenoid, remember, this is a power side switch circuit. If we look at the computer at this wire right here, this is a constant ground, and this up here is only a power whenever the computer closes the switch and sends a power to the solenoid. Now, here's where my question comes in. Where is the monitor for the circuit? Because I don't think you'll find it here on the ground side, because this is always going to be a ground. Even when you send power through the solenoid here and the solenoid is energized, this is always going to be a ground. Now, the other thing is that the monitor could be inside on this side of the computer. The only problem with that is that what is the computer looking for? Is it looking to see whether or not the pulse width modulated signal that it's generating is getting out of the computer? Because that certainly doesn't tell us anything about what's happening on this part of the circuit, because we could unplug the solenoid, the computer could be sending out a power through here, and if it's only monitoring itself here, then technically that should not set a code. I hope what I'm saying is making sense, and maybe I'm thinking a little too deep into this, but honestly, I'm just curious as to why the computer would set a P0010, which is a control circuit code. Now, the only thing I can think of, and this is just my opinion, because I have no factual proof to back this up, because I can't find any information on this, but my opinion is that more than likely, it's not looking at voltage, it must be looking at amperage. So maybe there is a monitor in the computer here, but it's not monitoring voltage, it's monitoring the amperage. Anyways, guys, I just wanted to throw that in there. I'll leave that up for discussion. Hopefully you guys have some good input, or maybe you guys have some factual information that you could share with the rest of us. If you do, go ahead and put it in the comments section. I'd really appreciate it. So with that being said, let's go ahead and move back to the vehicle. All right, guys, so moving back to the vehicle, we're under the hood. I've already gone ahead and removed the plastic cover so that we can get a good look at the solenoids. Now, if you look here, you'll see the two camshaft actuator solenoids. Now, the one to the front, which is closest to the intake manifold, is the intake camshaft solenoid, and the one on the back, which is closest to the exhaust manifold, is for the exhaust side. Now, to be honest with you, under normal circumstances, I would have already just replaced these solenoids because I know they're a common failure item, but for the sake of the video, we're gonna go ahead and do some testing using my lab scope. And I've already got my lead hooked up right here. Now what we're gonna do is we're going to identify the two wires. Again, if you look here, we have the two wires. This is the gray and blue wire, which according to the wiring diagram, this wire is our power feed that comes from the computer. And if you remember, this is a pulse width modulated power feed. And then on the other side, we have this violet and brown wire, and this violet and brown wire is going to be the ground side. So what we could do real quick is just back probe this ground side right here. I'm gonna go ahead and slide my back probe in there. And real quick, what I'm gonna do is I'm just gonna use the power probe. I do have it connected to the battery. And all I'm gonna do is I'm gonna touch it and I'm gonna see if we have a good ground. So touch it. As you can see, we're showing a good ground. So that shows us that the ground at the computer is good. Now we're gonna go ahead and move over to the power switch side. I'm gonna back probe this here. And right now we really shouldn't be showing anything on this. Maybe a ground because it goes back to the computer. So we touch it, I'm showing 0 volts. We're gonna go ahead and cycle the key on. Just gonna go inside the vehicle real quick and hit the on button. Let's go back under the hood. I'm gonna go ahead and reconnect the leads for my lab scope here. And if we look at the lab scope, all right, so looking at the lab scope, you'll see that we have 0.02 volts. Now this I actually believe is a bias signal, because let me show you what happens when we unplug this connector. I'm gonna go ahead and unplug this solenoid and just keep an eye on that voltage. I'm gonna unplug it. It's unplugged. You can see how it jumped up to 1.62 volts. Again, looking at the solenoid, it's disconnected, and I have my lead back probed to the power switching side. And looking at the lab scope, we show a bias voltage of 1.63 volts. I'm gonna go ahead and plug it back in and watch what happens. So when we plug this thing back in, you see it drop back down to 0.02. Now that may not tell us a whole lot, but it does give us an indication of how the computer is monitoring the circuit, because with that bias voltage, if there is an open in the circuit, let's say if the solenoid had an open internally, then this bias voltage would not have a path to ground and the computer would be seeing 1.6 volts. I think that in of itself would be enough to set a check engine light. Again, I'm not really sure. I just wanted to add that, but let's go ahead and start the vehicle up and see if we can get our pulse width modulated signal. All right, so we are inside the vehicle. I'm gonna go ahead and start it up real quick. Let's go back under the hood. All right, moving back under the hood. The engine is running, and you can see we have our pulse width modulated signal. I'm just on a 1 second time base, so you really can't see a whole lot of detail, but what we do know is that we do have computer control to the solenoid. Now we could also try to get a little more detail. Zoom in, see if I can set a trigger for this. All right, now I don't know if there's a whole lot that this signal can tell us, maybe other than the fact that the signal is actually reaching the solenoid, but it would be interesting to see if a signal like this would show signs of a voltage spike from a magnetic field collapse. Now, if you're familiar with auto air control systems that use a pulse width modulated signal, a lot of times you'll see a voltage spike at the end of the square wave, and that's indicating a magnetic field collapse, which is also a good way to determine whether or not we have current flow. Now, we could also switch over to the exhaust side and compare it, which I think is what I'll go ahead and do. Take a look at the lab scope. We pretty much see the same thing. Let me move the zero line up a little bit. Yeah, so we're pretty much seeing the same thing. I don't see any voltage spikes from any magnetic field collapses, so I don't think that's gonna help us as far as diagnosing the problem. I think probably what we need to do next is we're gonna go ahead and move this back over to the intake side, and we are going to connect two channels. One channel on the power switching side and the other channel on the ground. We are going to monitor both of them, drive the vehicle, and we're going to wait till the solenoid acts up. And whenever it does, we're going to see what's happening on the lab scope. So let's go ahead and do that. All right, guys, so I've got both leads connected and I've got them running inside the vehicle. Let's go ahead and take it for a drive. All right, so we're inside the vehicle, getting ready to go for a test drive. We've got the lab scope hooked up. We've got two channels. Our first channel is the control side, which is our power switching side, and the second channel is our ground. You can see up here, it's actually 0.03 volts. So let's go ahead and take it for a test drive. All right, so we're on the road. So far the vehicle seems to be driving okay. I'm just gonna keep driving it until it starts to act up. And hopefully we'll capture something on the lab scope. All right, guys, so I just got back from about a 15-minute test drive. And of course, the vehicle did not act up on me. I still have the lab scope hooked up over here. The signals still look normal. I haven't seen any glitches or any dropouts. I haven't seen any problems with either the power switching side or the ground side. Now I was really hoping to get this thing to act up so that we can prove that we don't have a problem with the integrity of the circuit when that solenoid starts to act up. But unfortunately, I'm just not going to be able to show you that, quite frankly, because the customer really didn't leave me with any gas. This thing's already below the E, so at this point I really just can't drive it any further. So I think there are probably a few other checks that we can do. We can probably go under the hood, and we can probably do a resistance measurement across the two terminals at the solenoid, which I think is probably what I'm gonna do next. So let's go ahead and go back under the hood. All right guys, so moving back under the hood. So you can see I've got my lab scope set up as an ohm meter, and I've already gone ahead and calibrated the leads. So I've got these two right here. So you'll see that when I touch them together, my meter goes down to 0. So now I'm gonna go ahead and I'm gonna touch the 2 pins on the intake solenoid. Now, unfortunately, I was not able to find an actual specification. I checked on all data, I checked on Mitchell. I could not find a resistance specification for the solenoid. So I think what I'm gonna go ahead and do is probably just compare the two. So let's go ahead and start with the intake side. Just gonna go ahead and take my leads, and I'm gonna touch both pins, just like that. We're gonna take a look at the reading on the ohm meter. Give it a second, let it auto adjust. Well, it kind of seems to be jumping around. Let me double check my connection here. Yeah, I'm on there. Take a look at that. It's jumping up to the mega ohm scale and jumping back down. So it's really not giving us a consistent reading. Well, it looks like it's holding it there pretty steady now. Somewhere around 15, 14 ohms. But then it starts to lose connection, kind of regaining connection, and I'm not moving my leads. I'm on there pretty steady, but it just seems to keep bouncing around. I really can't get a steady number on this one. Let's go ahead and compare it to the other side. I'm going to go ahead and touch my leads. We're now going to be looking at the exhaust solenoid. Let me get a good connection here, right there. Take a look at the reading. Looks like we're reading about 13 ohms of resistance. And immediately what I notice about this reading is that it's staying pretty steady. It's not jumping around like the other one was. Yeah, so around 13 ohms of resistance. Again, we'll go back to the intake side. Take a look at this one. All right, we're now connected on the intake side again. And once again, you can see our reading is all over the place. So this definitely looks like a bad solenoid. I think that's enough evidence to call this solenoid bad. Let's go ahead and replace it. All right guys, so we've got the new solenoid right here. Now what's real important is that you're gonna wanna put something, original equipment. This is an AC Delco product. So this is gonna be the original equipment. But before I install this, I'm gonna go ahead and do a resistance measurement on this new one. So I've got my leads right here. You'll see that when I touch my leads together, we show 0 ohms of resistance. I'm gonna go ahead and touch these 2 pins and see what reading we get. I'm touching both pins. Now if you look at the meter, we're reading about 10.8 ohms of resistance. This is on the brand new solenoid. So just for future reference, that's what the resistance is on a brand new solenoid. So if anybody's wondering what the specification should be and you can't find one, it's around 10.8 ohms. All right guys, so I'm gonna quickly replace this thing, kind of blow it out with air. Make sure you remove all the dirt and debris down in the valve cover because you don't want it getting inside. Now let's go ahead and remove 10mm bolt. And then we'll pry it out. Now these things can be pretty stuck in there. Well, this one came out pretty easy. And of course you're gonna get some oil. All right, now one of the things we want to look for with these solenoids is you want to make sure that we don't have any large pieces of debris or oil stuck in the screen. Also, you want to take a look at these screens, make sure that they hadn't come apart. I've seen some of these where pieces of the screen actually get trapped inside, but really that was more problematic on the earlier design. They used a different type of mesh. This is the newer type of mesh where it's a lot stronger. So just looking at this solenoid, doesn't look like it's clogged, doesn't look like the screen is damaged. It's probably just a failure with the internal coil winding of the solenoid. So we'll go ahead and scrap this one, install the new one. All right, so with the new one, you want to make sure you lubricate the O-ring with just a little bit of oil. We'll pop it into place. Pretty simple to do. Make sure you thread it by hand first. All right guys, so the torque spec for this thing is 89 inch-pounds, which is just snug. Now we'll go ahead and plug this thing back in, and we now have our new solenoid installed. All right guys, so we're back inside the vehicle. We've got the new solenoid installed. Got the scan tool over here. We're just gonna quickly clear the trouble codes. Clear DTCs. Yes. Let's go back in there, double check. No fault codes detected. You'll see our check engine light is gone. We'll try and take it for a quick drive, and we'll give the customer a call, have them come pick up the vehicle. Anyways guys, before I end today's video, I just want to take a minute to address a few things. I know that it probably seems like I'm overthinking such a simple problem, and like I said, I know these solenoids have a high failure rate. I've replaced more than my fair share of these things, and I'm pretty sure so have you guys. But I also think it's really important that we understand circuit design so that we can come up with new and different ways to test these systems. All I'm trying to do is provide you guys with some useful information and maybe some helpful diagnostic methods that you can use or apply to any vehicle. So hopefully you guys enjoyed the video. If you did find it useful or informational, please make sure you give it a thumbs up. If you enjoy the channel, please subscribe to the channel. If you enjoy these case studies, please make sure to check out my channel for all the other case studies I have. If you have any questions, you can always comment down below. Once again, thank you guys for watching, and I hope to see you in the next one.